And over the weekend, how many of you saw Princess Bride? You watched it again?
Yeah.
Yeah. As good as it always is?
Even better. And then I told my mom about Tubelin, and she thought it was really funny too.
Now, I had written up Maxwell's equations over there, now I've erased them. But so far, Maxwell hasn't contributed anything to them. So what does Maxwell actually do? We talked about the current in equals the current out. So if I take just a normal circuit here, now I look at a junction, whatever current's flowing into that junction is equal to the current flowing out of the junction. Matter of fact, I can take any point in a wire, and whatever current flows into that point of the wire, current will flow out. However, suppose I have a circuit with a capacitor. Yeah, I have current flowing into the capacitor, and I have current flowing out of the capacitor. However, if I look at a plate here, I have current flowing onto the plate, but I don't have current flowing off of this plate. And so this seems to violate Kirchhoff's junction rule, because I have current flowing into this point and not the same current flowing off of that point because there's a gap there. So we need to somehow resolve that. And this is Maxwell's contribution. Now, often when I do this, I go around in a circle and I end up somewhere where I started. Make sure I get this in the right direction. All right. So let's flash back. What is the electric field? So I've got my capacitor there. And we'll just make this the positive and negative ends. Right. What is the electric field between the capacitors? One too many lines. The electric field between parallel plates and a parallel plate capacitor. Some charge Q there. Negative Q there.
What are you asking?
It'd be the end of chapter 17.
It would, between the plates,
Yep.
that would be electric field plates.
I have no dielectric in there, so
No dielectric, okay, so then it would just be, this thing.
the sigma.
Over epsilon, which equals delta V over D. Is that
All right.
epsilon sub naught?
Doesn't be,
Sub naught is between the plates, but without the sub naught, it's just.
yeah, we don't have anything between the plates. So
Okay.
just sigma over epsilon naught. And what is sigma?
What is charge density? Surface charge density.
Yep. Which is,
Surface charge density. Charge divided by area.
yep. So this becomes Q over A epsilon sub naught. So what I'm concerned about here is while charge is building up on the plate, once charge is built up on the plate, then I have no, once I'm at maximum charge, I have no more charges flowing onto it, so I don't have to worry about what's coming off of it. So what I first want to start out with is look at the change in the electric field, which would be the change in Q over A epsilon sub naught. Well, the area of the plates isn't changing. Epsilon sub naught definitely isn't changing. So the only thing that's changing here is Q. So I have 1 over A epsilon sub naught times delta Q. I'm now going to figure out that, well, I know charge is building up on the plate over a certain amount of time, so I'm just going to figure out the rate at which it does that. So I'm going to divide by time. If I isolate delta Q over delta T, then I have epsilon sub naught A changing the electric field over changing time. I can distribute, I have this change in the electric field, I can distribute A through that, and so that would be the same as epsilon sub naught changing A epsilon naught. Over time. Obviously, I'm doing a little bit of hand waving here. A times the electric field is a quantity we've already talked about. What is the area times the electric field?
Gauss's law. Or Coulomb, yeah, Gauss's law of electricity. So, yeah.
I heard you say electricity. Electricity is a huge topic. This is one small aspect of it.
It would be. Wait, you said charge over?
No, area times the electric field.
It would be coulombs meters squared over seconds.
I'm not worried about units right now.
Coulomb's law.
It's part of Coulomb's law. It's the first part of Coulomb's law, but there's a name for this part just specifically.
Gauss's law of electricity.
It shows up in that. All right, I'm gonna spoil it for you. The electric flux.
Right.
So this is epsilon sub naught times the change in the electric flux over time. dq dt, what is that? That's another quantity that we've talked about. How much charge flows through a certain cross-sectional area in a certain amount of time? Like, too low. Good.
Now I'm second guessing myself.
Physics does that to people. Go for it. With confidence. The world be damned.
That would be voltage, right?
Yeah, not voltage. That's the last thing that you said. Erica, just go ahead and say it.
I don't know what it is. Amperes?
Those are the units. What is the quantity?
Oh.
Current, yeah. So that's just current. So we have a current here that's different from the traditional current, a current that's based upon the change in the electric flux. Well, I have a change in the electric flux because as current builds up on this, my electric field changes, and therefore the flux is changing. So this current here is not a traditional current. We give it a different name. We put a little subscript D there and call this the displacement current. So we will now correct or amend Ampere's law. So Ampere's law is that if I add up the magnetic field over some line, a closed loop, for those who've had calculus, a line integral of the magnetic field, he had that equal to mu naught I. We now tack on this other type of current, the displacement current. So we have the traditional current of just charges flowing, and then we have this displacement current. If I make the substitution over there, I get mu naught I plus mu naught epsilon sub naught, change in the electric flux over time. So this is Ampere's law with Maxwell's corrections, Maxwell's correction. And the implications of this, I don't know if you quite grasped yet, but this is very significant. Questions up to here before I talk about why this is of significance.
Is
Erica?
that an in naught before the epsilon's a naught, or is that another mu naught?
Here,
Yes,
that's mu naught epsilon sub naught.
okay.
Got both of them. All right, let's talk about the significance of it. So I've got D dot delta L, just rewriting what I have over there, I plus mu naught epsilon sub naught delta phi E over delta T, and then I have E dot delta L is equal to negative D. I take a charge and I move it over to here. I look at a spot in space here. My charge is initially in that direction and the electric field would point like that. I move the charge over to here and now my electric field is pointing in that direction. So we'll just call this EI initial and E final. EI initial was redundant. E initial, E final. My electric field changed. So as my electric field changed, my electric flux changed. So based upon this, since my so we have the electric field changes, causing a change in the electric flux. If the electric flux changes, I'm creating a magnetic field. That creates a magnetic field, not a delta V yet. Matter of fact, the rate at which I'm changing is changing. So I move the Q, but I start out at rest, I end up at rest, so I speed up and then I slow down. And so really, what's happening here is that the rate at which my electric field is changing causes a change in the rate at which the magnetic field is changing. So I'll have a change in the electric field, which causes a change in the electric flux, which causes a change in the magnetic field, which causes a change in the magnetic flux. A change in the magnetic flux causes an electric field. So if I take my charge here and I oscillate it back and forth, so it's constantly changing, then I'm going to have a change in the change in the change of the electric field, which causes a change in the change in the change of the magnetic flux, or the electric flux, which causes a change in the change of the magnetic field. Change in the change in the magnetic flux causes a change in the electric field, which then cycles back. So I can create the system here where I suddenly have this electric field creating a magnetic field, creating an electric field, creating a magnetic field. This, theoretically, is an electromagnetic wave. So what Maxwell did here is he figured out that we have this displacement current that exists based on a change in the electric field or electric flux. And so we get this cycle, we get a cycle going. So if I have an electric field that is constantly oscillating, well, if I get this charge moving back and forth, I can create an electric field that's oscillating up and down. The magnetic field that is created is perpendicular to this, which I offer without evidence, just letting you know. So this is my attempt at a three-dimensional drawing in two-dimensional space here. The purple line's supposed to be coming out toward you and away from you. So the electric field that is created, think about the actual magnitude of the electric field. It's oscillating up and down. And then my magnetic field is perpendicular to that. And so on. So all I have to do is have a changing electric field and it will self-propagate. And the next step is to actually figure out how fast is that wave going. Which we will do. But first, we need to talk about, in essence, a sine wave, or cosine wave, whichever one you prefer. We talked about this, so for when Erica returns for you. What math are you in?
I took college algebra.
Okay. So we've talked about this when we were doing harmonic waves, and that might be the time and place that you would have seen this. If I look at y equals sine of x, y, a sine curve will look like this, where that's 2 pi, pi over 2, 3 pi over 2. The basic sine wave, if you plug into a calculator, or if those are the values you would get, the magnitude here is 1. What I want to do is look at how y changes with respect to x. For those who have calculus, the first derivative. For those without calculus, the slope. So when I have a curve, how do I find the slope of a curve? slope of a curve. How do you find the slope of a line?
You just do one on the line.
Take 2 points, and then,
You can slope one, y two minus y.
okay, yeah, change in y over change in x. So this is why, because I'm looking at how y changes with respect to x, this is what we're looking at right here. This is the slope formula. So to find the slope at that point, you draw a tangent line and find the slope of the tangent line. At this point, at the top, find the slope of that. So you're basically, the slope is constantly changing. Where is the slope of this equal to 0?
Here is the slope of that equals zero.
That's the question.
At the top, the peak.
Pardon?
At the peak.
Okay, yeah, at the peak, so right there, the slope is 0, and,
Valley.
yeah. So pi over 2 and 3 pi over 2. All right, this first section right here, is that slope positive or negative?
Positive.
Okay? And then this region from here to here,
Negative.
and then from here to here.
Positive.
So it looks like that. And this is just the cosine of x. Again, you go into a calculator, you just type in numbers from 0 to 2 pi, that's what you get. Obviously, x is in radians. If I did the slope again, so the slope of delta y over delta x, which can be written in a shorter notation of just delta squared y over delta x squared. That's those. Who's that calculus? Okay.
And it's still.
All right. So the second derivative of y with respect to x. In other words, I'm doing the slopes of the slopes. Where is the slope of this equal to 0?